Hi, this is Max Liu, and this is my submission for Lab 1 Constant Velocity for Physics 2211. Here are the things we're going to go over today. So a brief introduction. The purpose of this experiment is to observe the motion of the object moving at the same speed without any changes in direction. The object that will be observed is a marker rolling across a flat surface at constant velocity. And the program tracker will be used to record the position of the marker, and the experiment will show the Newton's second law, or the momentum principle, and analyze the data of the real world and computational model. So here are the preview of the results. You can see that the observed data appears to diverge off from the predicted data as time goes on, showing that there are some external forces acting on the object. In Newton's first law, an object in motion will stay in motion unless acted upon by an external force. In the case of the marker, there should be zero net force acting on it, so it should have constant velocity. Newton's second law describes the relationship between the force and between the force acting on the object and the result of the motion of the object. So for the marker to move at constant velocity, its net force must be zero, meaning that the object is not accelerating, and so the sum of all forces is zero. And then the image describes Newton's second law, F equals ma, and this equation can be used to get the velocity update formula, which is v final equals v initial plus f net delta t over m. This equation will be used to predict the position of the marker in the computational. Okay, so here's the video. As we can see, the system is the marker and the surroundings is the table, and the initial position is shown here, and then the initial velocity is 0.132 meters per second. I calculate average velocity by taking the position on frame 1 and subtracting it from the position on frame 0, and then dividing by the time between those two to get 0.312 meters per second. Closed script code, I have the ball's mass be unchanged, and then the ball's position be set to the initial position found in tracker, and then the initial velocity was the one found in the previous calculation, and then t is set equal to 0, and then delta t is set to 0.033. Then the while loop will run for 1.4 seconds, because that's how long the video ran for in tracker. And then the net force is 0, since we're assuming 0 net force. And then the velocity update formula is used to change the velocity. And then the ball's position will be updated using the position update formula shown here. Okay, I got this graph by putting together the observed and computational data into an Excel graph. So the similarities are that both of them are upward sloping. The differences start to show as time goes on. The position of the observed data diverges from the predicted position. And some possible errors that may have caused this is the friction from the table, or due to human error from setting up the tracker software to get the position of the marker. To address what if the y-axis or x-axis were flipped through tracker, so if the y-axis were flipped, it would have a negative y position, so it would have the lines would slope downwards and to the right. And then if the x-axis were flipped to be the negative x, it would be like this. It would point up and to the left, but still downward sloping. And my results will not change because we're looking at the magnitude of the position, so it would still be the same. Is it possible to know how many pushes or pulls to get zero net force? I attempted to push the marker across the table at constant velocity. However, there are other factors affecting the system and the surroundings. There's friction that's between the marker and the table, which would cause variation seen in the data. So it would not be possible to know how many pushes or pulls to get zero net force. So in conclusion, the experiment was conducted to show Newton's first and second law, and then tracker was used to record the position of the marker while rolling across the table. And then the results of the experiment show external forces in the surroundings, such as friction, are potential causes for differences in the observed and computational models.